Welcome back to Lesson 10 of our overview of the course Networks and Distributed Systems. This course is based on the text by Jim Caros and Keith Ross titled Computer Networking, a Top-Down Approach, 6th edition. In the last lesson, we were discussing throughput and the layers used to apply the general systems approach to network design. So let's pick up where we left off. Back in the 1970s, the International Organization for Standardization, ISO, proposed that computer networks be organized around 7 layers called the Inter-Systems Interconnection Model, OSI. The model began with the protocols that were to become the Internet protocols just being developed. This was before most people even thought that we would have anything like the Internet we use today. Nevertheless, beginning in the 1970s, many training and university courses picked up on the ISO mandate and organized courses around that 7-layer model. This was at a time when the closest thing we had to the Internet were the local bulletin boards that many of us used to share utilities and games with the other geeks in the neighborhood. Because of its early impact on networking education, the 7-layer model continues to linger on in some networking textbooks and training courses. The 7 layers of the OSI reference model shown here are application, presentation, session, transport, network, data link, and physical layers. Functionality of 5 of these layers is roughly the same as their similarly named Internet counterparts. The role of the presentation layer is to provide services that allow communication applications to interpret the meaning of the data exchanged. These services include data compression, data encryption, as well as data description, which frees up the applications from having to worry about the internal format in which the data are represented, format synchronization of data exchange, including the means to build checkpointing and recovery scheme. For our purpose, we'll be examining network communication along the arrangement of the 5-layer model. This slide shows the physical path that data takes down a sending end systems protocol stack, up and down the protocol stacks of the intervening link layer switch and routers, and then up the protocol stack of the receiving end. Routers and link layer switches are both packet switches. Like the end systems, routers and link layer switches organize their networking hardware and software into layers. But routers and link layer switches do not implement all the layers in the protocol stack. They typically only implement the bottom layers. These intermediate switches are only required to forward packets to the end systems or destination host, and therefore do not need to perform the task of the application or TCP layers. For instance, remember that the link layer switches only function on autonomous networks and therefore have no routing responsibilities. On the other hand, routers implement layers 1, 2, and 3. This means, for example, that internet routers can implement the IP protocol, a layer 3 protocol, while link layer switches cannot. By the way, we're numbering these things from bottom up. We'll see later that while link layer switches do not recognize IP addresses, they are capable of recognizing layer 2 addresses, such as Ethernet addresses. Note that hosts or end systems implement all 5 layers. This is consistent with the view that the Internet architecture puts much of its complexity at the edges of the network. This slide also illustrates the important concept of encapsulation. At the sending host, an application layer is passed to the transport layer. There it goes. That's the M that we see here. In the simplest case, the transport layer takes the message and appends additional information. This is information that the layer providing the service needs for use by the receiver side transport layer. This is the so-called transport layer header information. The application layer message and the transport layer message information together constitute the transport layer segment. The transport layer segment thus encapsulate the application layer message as we see here. The added information might include information allowing the receiver transport layer to deliver the message up to the appropriate application. And it might include error detection bits that allow the receiver to determine whether the bits in the message have changed en route. The transport layer then passes the segment to the network layer. The network layer adds network layer header information. The H seen here includes things like the source and destination in-system addresses, and this creates the network layer datagram. The datagram is then passed to the link layer, which of course will add its own link layer header information and create the link layer frame. Therefore, we see that at each layer, a packet has two types of fields, header fields and payload fields. The payload field is typically a packet from the layer above. And understand that at each layer, it has no idea what those bits it received from above represent. All it does is encapsulate them, add its own header information to each unit, and sends it on. You'll notice that at each layer the payload takes a different name: message, segment, datagram, and frame. The general term for all of these packages is Protocol Data Unit, or PDU. For example, the PDU of the link layer protocol is the frame. The PDU of the network layer protocol is the datagram, and so on. The process of encapsulation can be more complex than I just described. For example, a large message may be divided into multiple transport layer segments, which might themselves be divided into multiple datagrams. That's because each layer protocol has its own limits on the size of the PDU. So, if the bundle being sent down is too large to fit the protocol data unit of the layer protocol that's doing the processing, then it must break the downward flowing bundle into smaller pieces so that its counterpart at the other end can handle them. That suggests that the header information not only includes information normally needed, but it also must contain a sequence in order for the receiving unit to reassemble the data for the layer above. At the receiving end, such a segment must be reconstructed from its constituent datagrams. Usually that's just a matter of stripping off the header and passing it on up. Let's watch it as it proceeds. It's moved over to the first link, and then it hits the switch in the router link layer passes it up to the router network layer, where it passes it on to the destination, and then over the destination you see that it made it all the way back up to the application layer. In other words, the headers were all stripped off as it came up to the application layer. Well, that concludes our coverage of the layers. Let's take a break now and take care of any assignments that you may have. And when you're ready, come on back for the next lesson in the series.